Hello everyone, how are you? I hope you are all doing well. So in last lecture we have studied about electric field due to a uniformly charged non-conducting solid sphere at the points which is outside the solid sphere and at a point which is on the surface of the sphere. Now in today's lecture we are going to study the electric field inside the solid sphere. So due to some technical issue, the connection was lost in the last lecture, so it was left. So let us start with uh, the concept that there is a solid sphere. Let us say there is a solid sphere. There is a solid sphere of radius r. Its radius is r, and it is positively charged. All over, we can say, all over its volume, the positive charge q is given. The charge q is given to this solid sphere, and the type of this solid sphere is it is non-conducting. And now we are going to assume a Gaussian surface to find out the electric field inside the solid sphere. So let us assume that there is a Gaussian surface of shape shape spherical, and the radius of the Gaussian surface is r, where r is, okay, I'm assuming the case electric field electric field inside the solid sphere. What will be the electric field inside the solid sphere? So first of all, for that, we have to use the application of Gauss law. So application of Gauss law. What is the application of Gauss law? As we know that we use Gauss law to find out the electric field due to some symmetrical objects, and we find out that what is the electric field due to those, we can say, symmetrical objects, and how the electric field depends on the distance from the center of those symmetrical objects like cylinder, or we can say this sphere or spherical cell. Now the Gauss law says that the electric flux passing through any surface, it can be stated mathematically as integration closed integration over E vector dot ds vector equal to q enclosed upon epsilon naught, where this q enclosed is the charge enclosed by the assumed Gaussian surface. So here we have assumed the Gaussian surface inside the solid sphere. So we can say that the net total charge, which is q, it will not be, we can say, accumulated in the smaller sphere which is inside the bigger sphere. Some fraction of it will be, uh, we can say, it will be there in the smaller sphere. So we have to find out that. So first of all, for that we know that this solid sphere is uniformly charged. The uniformly charged means the charge density is same for every point in, we can say, for every point or every fraction of this solid sphere. So now, as we know that the density is constant, so the density of the bigger sphere and the density of the sphere which we have assumed, the Gaussian sphere which we have assumed, will be same. So since since the sphere is uniformly charged, uniformly charged, so its density is same for smaller and bigger bigger spheres. Now the density for the bigger sphere will be the net charge upon the total volume of the bigger sphere. So 4 by 3 pi r cube. Now, the charge included or the charge enclosed by the smaller sphere is q enclosed, and the density of that, the volume of that sphere will be 4 by 3 pi r cube, where r is less than capital R. Now, this 4 by 3 and 4 by 3 will be cancelled out, and we will get q enclosed equals to q into r cube by r cube. This will be the charge enclosed by the smaller sphere which we have assumed. Now we can place it in the equation. Let us say this is equation number 1. Then from the equation number 1 we can say that from equation 1. So when we put this in equation number 1, so we will get E vector dot ds vector equals to q into r cube upon capital R cube. Now, as we know that the electric field due to a positive charge is always radially outwards. So that is why for this given case also, uh, we can say it is a spherical, it is a solid sphere. So that is why the positive charge is uniformly distributed, and the electric field due to this positive charge will be uh, will be producing the electric field radially outwards, and and the we can say the area vector of the solid sphere will also be with we can say along the electric field, because they both have the same direction, radially outwards, and therefore the angle between electric field and the area vector is 0 degree. And that's how we can write it, like E dot ds cos 0 degree equals to q r cube upon capital R cube, where capital R is the radius of the bigger sphere. Now, since cos 0 is 1, and E dot ds will give us the value E into the integration over ds will give us the value, the surface area of the smaller sphere. So it will be 4 pi r square and equivalent to q r cube upon r cube. Now we will get sorry, one mistake is there. We have forgot to mark epsilon naught in the denominator part. So it will be from this equation. So epsilon naught is also there. So epsilon naught. Now the equation will be E equals to q r cube upon 4 pi epsilon naught r square into r cube. Now this r square, in the numerator we can see that it is r cube, and in the denominator it is r square. So in the numerator only r to the power 1 will remain. So electric field will be E equals to q into r upon 4 pi epsilon naught r cube. This is the electric field inside solid sphere, and as we can see that its dependency is E proportional to R. It is E proportional to R. Or in the vector form, if you want to write, so it will be in vector form, we can write it like E vector equals to Q into R upon 4 pi epsilon naught r cube into r cap. So this will be the electric field due to a solid sphere at a point inside the solid sphere. And the dependency is, we can see that it is E proportional to R. The electric field is directly proportional to R. So that is why we can say that the graph between electric field and the distance from the center of the solid sphere will be a straight line. Since it is a straight line, we can say they are directly proportional. So that is why the graph, if we draw, it will be, so if on the horizontal axis, if we take R, and on the vertical axis, if we take the electric field, then the graph between them will be a straight line. It will be a straight line. So that's what the graph between electric field and the radius of the small, we can say the smaller sphere. Now, if we merge the graph for all the cases, then we can draw a graph, since we got in the last lecture that the electric field outside. What is the electric field outside? Electric field outside the solid sphere is, it is E equals to Q upon 4 pi epsilon naught R square. And if we write the dependency, then it is E proportional to R. Sorry, E proportional to 1 upon R square. Or we can say that electric field is inversely proportional to the square of the radius of the Gaussian sphere, which we take, uh, the bigger Gaussian surface, which we take for the solid sphere. And the graph for this portion will be where R is greater than R. It will give us the electric field such as, 1 second, electric field such as this kind of graph you will get. And if we merge the equation, this we can say the graphs, both the graphs, then we will get the graph such as, since we know that for the inner, we can say when the radius of the Gaussian sphere is less than R, so it will be a straight line. So the graph will be straight line for the initial values. And after that, this type of graph we will see. So it will be this type of graph. One second, it is not properly made. This type of graph you will see. And this point will be where the R reaches the value equivalent to capital R, where R is equal to capital R. And so that is why we can say that for this portion, E is directly proportional to R, and for this portion, E is inversely proportional to R square. So that is how the graph between the R and the electric field looks like. I hope you got the idea. If you still have any doubt, then you can ask in the comment section. I'll try to help out. Thank you so much for watching this video.